Hi guys, I'm gonna go over 6.3 in this video. We've done a lot of 6.3 in the Zoom session yesterday, but I'll just quickly also give a summary of that and maybe do a little bit more over here. So 6.3, what we're considering is sums of independent random variables. We've looked at independent random variables in 6.2, so you know what that is. You have that two random variables are independent if the probability of two random variables x and y are independent if the probability of x in A and y in B is the probability of x in A times the probability of y in B. Okay, and we saw what that means for the mass function or the distribution or the density in case of continuous. We've seen what all that means. Okay, so now we're gonna see if you have two random variables that are independent, how does the sum behave? Okay, all right. So x and y independent, and let's just stick with the continuous case. With their densities, with the PDFs, f sub x and f sub y respectively. Okay. Okay, so then let's see how x plus y behaves. So first let's look at the distribution of x plus y. And the CDF of x plus y, so that is the probability x plus y is less than or equal to A. We write it shorthand as f sub x plus y evaluated at A. Okay, so what is this? Well, if you look at the plane, okay, and just pick any A, if you want, pick a positive A, pick a negative A, doesn't matter. So if you look at the line x plus y equals A, that's just y equals A minus x. So that's a line with slope -1 with y-intercept equal to A, like this, if A is positive, or over here if A is negative, doesn't matter. So what we want is x plus y less than or equal to A. So we want, that's the same as saying, this is the same as the probability of x comma y as a point being in that set. Okay, I'm just showing you pictorially what that means. All right, so how can we write that down as an integral using the joint density? Okay, so that would be an integral. What's the range for y? Y can be anything. So y goes from minus infinity to infinity. So what I mean to say is there's no limit on the y, right? Just like you did in Calc 3. You would have, in this region, y can be as small as -1 trillion or as large as 1 trillion or any, there's no limit. So the range for y is just minus infinity to infinity. If you fix a certain y, okay, so fix a y, then for a fixed y, let's call it y naught, what is the range for x? X can go from minus infinity all the way till this point on the line. What is that point? That will be, so that is x plus y equals A, so the x is A minus y. So whatever be the y, it's A minus y. So if it's y naught, it's A minus y naught. If y is 3, it's A minus 3, and so on. So for any fixed y, you have that x goes from minus infinity to A minus y, okay? And what are we integrating? We're integrating the joint density. The inside was the x limit, so dx, and then dy. But they're independent, so what is the joint density? The joint density is the product of the individual densities. Okay. Well, in the integral, this has got nothing to do with x, so let's pull that out. And you have a f sub y of y outside, minus infinity to a minus y, f sub x dx. and dy. All right, so what do we have over here? This is the probability that x is less than or equal to a minus y, right? That is just f sub x evaluated at a minus y. All right. So the integral turns into integral f sub y at y times capital F sub x evaluated at a minus y integrated from minus infinity to infinity. Okay, so you may have seen this in a differential equations class. What is this? You have that the CDF of x plus y, this is the convolution of f sub y and capital F sub x, or you could have it as little f sub x and capital F sub y. Okay. All right. And now, if you differentiate this, okay, so we have that this is f sub x plus y evaluated at a is this. All right. Now, if you differentiate this, what do we get? So let's differentiate the capital F sub x plus y. So dda of f x plus y at a, derivative of the CDF is the PDF. Okay. X plus y is just one number. So x plus y is a random variable whose range is on the real line. All right. Then what is this? This is the derivative of the right. Let's differentiate that. Okay, and over here, we can, because of the niceness of the functions, pull that in. This integration is from minus infinity to infinity. F sub y of y has nothing to do with the variable a, so this will just be left with the derivative with respect to a of capital F sub x at a minus y. What will this be? This is just going to be capital F prime sub x, which is little f sub x, evaluated at a minus y, times the derivative of a minus y, which is just 1. So we just have, this is the integral from minus infinity to infinity of little f sub y at y times little f sub x at a minus y. So this is the PDF of x plus y. Okay. Of course, you could switch the roles of x and y. You could also write this as minus infinity to infinity of x, f sub x at x, f sub y at a minus x dx. Okay, it's the same thing. Both of them are correct. All right. So next, let's come to these things called IID, okay? Identically distribute, actually, first let me just mention what IID random variables are, okay? IID, you'll hear this word a lot. This is identically distributed independent random variables, okay? Or independent identically distributed random variables. Let's just write it that way. Okay. So what are IID random variables? So what you have is you have random variables that are independent. So one's outcome will not affect the other. And the distribution of the random variables is identical. Okay. So you have, for example, I roll a die, a fair die, and you do. That's both of us. We're rolling a fair die, and the distribution of what you get and what I get, it's identical. All right. Okay. So that's identically distributed in independent identically distributed random variables. All right. So in 6.3.1, we have identically distributed uniform random variables. Okay. All right. And what you can get from over here is if x and y are uniform on 0, 1. Okay, so let x and y be independent random variables that are both uniformly distributed on 0, 1. Calculate the PDF of x plus y. Okay, so what we can do actually is just use the formula from above, and we know that the PDF of x plus y at any number a will be the integral from minus infinity to infinity of f sub y at a, I'm sorry, not at a, at y, times f sub x at a minus y dy. All right. Okay, so we want to use this, but before that, let's stop for a second and ask ourselves, what is the range of x plus y? Well, x can be anything from 0 to 1. Y can be anything from 0 to 1. So the range of x plus y will be 0 to 2. All right? So you can say right away, right now, that, f sub x plus y at a is 0 if a is not in the set 0 to 2. All right? Okay, so how about when a is in the set 0 to 2? We're going to do this in two separate ways, okay? So if a is in 0 to 2, okay? So case 1, a is in the interval 0 to 1. Okay, well, let's look at the integral. F sub x plus y at a, in the first place, just generally, is just minus infinity to infinity. F sub y of y, f sub x sub a minus y dy. Well, you know, this is, y is uniform 0, 1. So that's going to be 0 outside of the interval 0, 1. And it's 1 inside the interval 0, 1. So you know, in fact, this has got nothing to do with a. This is also true when a is in 1 to 2. You have that f sub x plus y at a is the integral of the density of x evaluated at a minus y. Okay, well, let's take a look. Now, what happens with the density of x evaluated at a minus y? A is in the interval 0 to 1. Okay, so you have that a is in 0 to 1, and you want to look at f sub x at a minus y. Okay, well, f sub x is 0 if, or actually let's just write t, if t is not in 0 to 1. Okay, so what do you need? You need that a minus y should be in 0 to 1. Okay, so that is a minus y less than or equal to 1, bigger than or equal to 0. Correct? So what do you need? You need that the value y is less than or equal to, just adding the y, less than or equal to a, less than or equal to 1 plus y. But this is always going to hold true because you know that a is in 0 to 1. So a is always less than or equal to 1. So this tells you that y needs to be less than or equal to a. This is a dy integral. Y goes from 0 to 1. But if y is bigger than a, you know this is 0 from this little calculation. So you know y needs to be less than or equal to a for a minus y to be in 0, 1. If a minus y is not in 0, 1, that's 0 and there's nothing to do. Okay? So you have that y is... And that will give you 0. So you only have to restrict yourself to y less than a. And this is f sub x. Sorry, not y a. Y has to be less than a. And you have 1 dy. And this integral is just a. Okay. Now let's take the case where a is in 1 to 2. All right. Then what do you have? You have f sub x plus y at a. It's the same thing. Integral 0 to 1. F sub x at a minus y dy. All right. Same thing. You know f sub x at t is 0 if t is not in 0, 1. Right? So if t is less than 0 or bigger than 1, you have that this guy is 0. All right. So you need a minus y to be in 0, 1. And if it's not in 0, 1, then we wouldn't even include it in the integral because that's just 0. Okay, so a minus y is less than or equal to 1, bigger than or equal to 0. Okay, and what do you have? Now, once again, what you do is add y throughout. And you have y less than or equal to a less than or equal to 1 plus y. Okay, hang on. And we want to try and get a hold of what's going on with y. Well, this we don't. Now this side's not going to give us any information because you know y is always going to be between 0 and 1. All right, but a is always bigger than or equal to 1. So this side's useless. So we have to consider this side to give us a bound on y. So now you have a less than or equal to 1 minus y. So a minus 1, subtract 1, less than or equal to y. So in this situation, when a is from 1 to 2, the restriction is a minus 1 is less than or equal to y. And if that is not satisfied, the function you're integrating 0 and it's not going to contribute anything. So you will go y, minimum value is a minus 1. Of course, maximum value is 1. And you have 1 dy. And this integral is 1 minus a minus 1. So that is 2 minus a. Okay. So this was just something we did to find out what the limits are. Okay. All right. So we have f sub x plus y at a. What is this? It is a if a is between 0 and 1. And it is 2 minus a. Or you can just, here, actually, let's just write it. It doesn't matter which one you include the 1 in. And actually, let's put less than or equal to. And it is 2 minus a if a is bigger than 1 and less than 2. And it is 0 otherwise. Okay? So that tells you what the density of x plus y equals. And if you look at the graph of this, what this is from 0 to 1, it is just a. And from 1 to 2, it is 2 minus a. So this is what the graph looks like. Okay. All right. And you can also talk about what happens when you have more than 2 independent uniform random variables that you're adding up. Okay. You can take a look at that in the book. Okay, so what we're going to do next is sums of independent normal random variables. We're going to skip 6.3.2, the gamma random variables, okay? just mainly for the lack of time. All right, so 6.3.3 is where we're going. What we're looking at over here is sums of independent normal random variables. And the main result you have is that if you have independent normal random variables, then and you add them up, what you have as a result is also a normal random variable, and the mean of the sum will be the sum of the means, and the variance of the sum is the sum of the variances. Okay, so let's write that down. Proposition 3.2. I'm not gonna prove it over here. You can take a look at the proof in the book. It's done in 2 parts. Okay, proposition 2.3.2. So if xi, I equals 1 through n, are independent normal random variables, with respective means and variances, with their respective means and variances being mu I and sigma I squared. Okay. Okay, then you have that there's summation sigma summation xi, I going from 1 to n, is a normal random variable with mean, which is equal to the sum of the mu i's, and the variance equal to the sum of the sigma i's, with mean and variance. Okay, and the proof is done in 2 parts. It mainly uses the fact that the PDF of the sum is the integral of f sub x at a minus y times f sub y at y. It's a result we proved at the beginning of this video. And you then integrate that, and it turns out that once you integrate that, the density of a sum is exactly the density of a normal random variable whose mean is the sum of the means and variance is the sum of the variances. Okay, I'm not gonna show you the proof of that. You can take a look at it in the book, like I said. Okay, what we will look at is example 3C from the book. All right. Okay, so what is example 3C? A basketball team will play 44 games in a season. 26 of these games are against Class A teams and 18 are against Class B teams. Suppose that the team will win each game against Class A team with probability 0.4 and will win each game against the Class B team with probability 0.7. Suppose also that the results of the different games are independent. Approximate the probability that the team wins 24 games or more in all. The team wins more games against Class A teams than it does against Class B teams. Okay, so what do you have? You have that the team will play 44 games, okay? Out of these, 18 are against Class A teams. Okay, and you have that 26 are against Class B teams. Oh, I mixed up the numbers, sorry. 26 are against Class A teams, and 18 are against Class B teams. Okay, probability that any particular game a probability that game against Class A team is 1 is 0.4, and probability that game against Class B team is 1 is 0.7. Okay, the question 1 says probability, what's the probability that team wins more than or at least 25 of these 44 games? And part B asks, what's the probability team wins more against A than B? Okay, so that's what we have. All right, so what do you, just take a look at this situation. The team's gonna win, play 26 games against Team A. And each one of those, it will win with probability 0.4 independently of any other game. So that is a binomial random variable, the number of games it wins against Team A. And then the number of games it wins against Team B, that also is a binomial random variable. And over here I forgot to say, it's approximate the probability. Okay. Now, you're asked about the total number of games that the team wins in all. All right, so you're asked about the random variable x plus y. Okay. Now, really, x and y by themselves are binomial. And if you try to do this as a binomial random variable, that is going to get very, very tedious. You know, just one by itself. Let's suppose the team wins 25 against Class A team and 0 against Class B. Or it could be 24 against Class A and 1 against Class B team, and so on. There's so many of them. You'd have to add up. Each one of them is a binomial random variable with crazy powers and stuff. High factorial, so it's better not to do it this way. It's better to do it as normal approximation. Yes, you do have, in this case, that the numbers are not that big, but still you have to do it as normal, otherwise the calculations are crazy. So let x sub A be the number of games team wins against Class A teams. Okay, I'm just going to shorthand and write this. XB is the number of games team wins against Class B teams. Okay, what part A you're asked, or actually before that, let's just write XA is binomial. It's truly binomial with n equals 26, b equals 0.4. Okay, so you can say XA is approximately normal with mean, let's call it mu sub, let's write mu sub A is 26 times 0.4, okay, which is 10.4, and variance is 26 times 0.4 times 0.6, which is 6.24. All right, and you have that x sub b, that's truly binomial, n equals 18, p equals 0.7. But you know that in this case too, you have this is approximately normal. The double squiggle means approximately. The single squiggle means this has the distribution of. Mu sub b will be 18 times 0.7. So that will be 12.6. And sigma squared sub b is 18 times 0.7 times 0.3. So that's 3.78. All right. And what we're asked in part A, the probability that x sub A plus x sub B bigger than or equal to 25. All right. Okay, what can you tell me about x sub A plus x sub B? Well, you know each one is normal. In fact, any one game is independent of the other. So totally x sub A and x sub B are also independent. So you have that x sub A plus x sub B will also be approximately normal. What will the mean be? It'll be the sum of the means. And what will the variance be? It'll be the sum of the variances. Okay, so the mean is 23 and the variance is 10.02. Okay. All right, so now you can work this out. P of x sub A plus x sub B bigger than or equal to 25. Subtract, before we do anything, okay. We are approximating a discrete random variable with a continuous random variable. We are approximating binomial with normal. So what do we need to do? We want to include the bar for 25 and there's a bar for 24. So what do you want to do? Whatever be the normal curve, you want to count the area to the right of that line. So if you want to think of it that way, probability of x sub A plus x sub B bigger than or equal to 24.5. Make sure you do the error correction. Okay, and now you can subtract the mean and divide by the standard deviation on both sides. Okay, and now x sub A and x sub B were not normal. They were approximately normal. So I now will put a double squiggle when I call this approximately Z. And this turns out to be 1.5 over 10.02. Oops. Under the square root. And this is approximately 0.474. Okay, so this is 1 minus phi of 0.474. Okay, so the answer is approximately 0.3178. All right, so much easier to do it this way. The other way, you'd probably need to make an Excel spreadsheet. All right, now part B. In part B, you're asked what's the probability it wins more games against Team A than Team B. Okay. Okay. Well, let me write this down as a inequality with random variables all on one side. Okay, so that is the probability x sub A minus x sub B is bigger than 0. Well, bigger than 0, these are integer valued. So x sub A minus x sub B is also going to be integer valued. So bigger than 0 would mean bigger than or equal to 1. And bigger than or equal to 1, you want to include this whole bar. So that's the probability x sub A minus x sub B is bigger than or equal to 0.5. Well, why did I do that? Well, once again, we're going to use that x sub A is binomial. Okay. X sub B is binomial. X sub A is approximately normal. X sub B is approximately normal. So what do you have? Normal times any number is also normal. So since x sub A is approximately normal, since you have x sub B is approximately normal, we can also say minus of x sub B is approximately normal. Because normal times any number is also still going to be normal. So if you multiply it by -1, you still have normal. So if you add these two now, we can apply the result from before. Sum of normal, independent normal is normal. So you will have that this is approximately normal. Okay, so x sub A minus x sub B is approximately normal. And what is the mean? The mean will be mu sub A minus mu sub B. So that is, let's remind ourselves, 10.4 and 12.6. So that is negative 2.2. And variance, the variance is going to be the sum of the variances because it's sigma sub a squared plus negative 1 squared times sigma sub b squared. So it's still just the sum of the variances, and just as before, you'll have 10.02. Okay? And now we can just use the above. Continuing over here, we have the probability x sub a minus x sub b, or x sub a bigger than x sub b, strictly bigger than, is probability of x sub a minus x sub b is bigger than or equal to 0.5. All right, now we'll subtract the means, divide by the standard deviation, and so on. So you'll have probability x sub a minus x sub b minus of negative 2.2, so plus 2.2, divided by square root 10.02 is bigger than or equal to 0.5 minus of negative 2.2, so plus 2.2 divided by square root 10.02, and this is approximately z, so you write approximately probability z bigger than or equal to 2.7 over square root 10.02. Okay, and actually let's just write it in here. This is approximately 0.8530. Okay, and so this is 1 minus phi of 0.8530 approximately. That is actually let's just write that equals, because that is not exactly this, I put an approximately sign, and this will approximately equal 0.1968. Okay, so that's quite neat that you could use normal approximations to calculate what otherwise would have become a very, very tedious problem. All right. Okay, so let's do one more example with this normal approximation. Okay, and that is example. Actually, we'll do one more example. Okay, 3D. Now in 3D, what we're going to look at is log normal random variables. All right, what is a log normal random variable? Actually, let me write down the definition up here. A random variable y is said to be log normal with parameters mu and sigma squared if log of y is normal with mean, mu, and variance sigma squared. Okay, so you say a random variable is log normal if log of it is normal. All right, so let's take a look at an example using this. So let S, starting at some fixed time, let Sn denote the price of a certain security at the end of n additional weeks. Okay, so Sn is the price after n weeks. A popular model for the evolution of these prices assumes that the price ratios Sn over Sn minus 1 are independent and identically distributed log normal random variables. Assuming this model with parameters mu equals 0.0165 and sigma equals 0.0730, what's the probability that the price of the security increases over each of the next 2 weeks? B, the price at the end of 2 weeks is higher than it is today. Okay, so let's take a look. So you have Sn is the price of the security after n additional weeks. And you know that Sn over Sn minus 1, for the different n's, these, you take these, okay? These are independent log or identically distributed. log normal random variables with mean mu and variance sigma squared, okay? And what is mean? In this case, you're told that this is 0.0165 and sigma squared is 0.730 squared. All right. Okay, so in part A of the question, they're asking the price of the security. What's the probability that the price of the security increases over each of the next 2 weeks? Okay, so probability price increases over each of the next 2 weeks. All right, so first what we're going to find out is what's the probability that it increases over 1 week. All right, so we want the probability that price over next week is bigger than price today. All right. We don't know about anything about the SIs by themselves, but we know how the ratios behave. So we will rewrite this as S1 over S0 is bigger than 1. Okay, we know this. That is log normal. So what we will do is take a log on the inside over here. And log is increasing, so you just leave the inequality. A bigger than B means log A bigger than log B. And this is 0. Okay. And this you know is normal with the mean of 0.0165 and the sigma squared of 0.0730. Okay, so what we're going to do is subtract its mean and over here, we're not doing anything discrete. You know, price is a continuous thing. So we don't have to do any error correction. Okay. And now that this was normal, so now when you subtract the mean and divide by the standard deviation, it becomes normal 0, 1. And what will this value be? Okay, let's just... and that is approximately 0.2260. So this is approximately 1 minus phi of 0.2260, and that is approximately 0.5894. Okay, so the probability from 1 week to the next, the probability that the price increases is 0.5894. You're asked for the probability that it increases from this week to the next, and then once again from next week to the following. And what do you know? You know that these ratios that you have, SI over SI minus 1, they're independent from any 1 week to the next. So you know that the probability will be, for the next 2 weeks, will just be the square of these. Okay, so probability price increases which is approximately 0.3474. Okay, so that's the part A. All right, now in part B, what are you asked? The price at the end of the 2 weeks is higher than it is today. So you want the price at the end of 2 weeks is higher than it is today. Okay. All right, well, this is a jump of 2 time periods. But anyway, let's write it down as a ratio because we know how ratios behave. And then we'll see how we can fix it. Oops, that's a 1. Okay. What can we do with this? We don't know about S2 over S0. We do know about S2 over S1. So we can play a little trick. Let's write this as S2 over S1 times S1 over S0. You see, all we did is multiplied by S1 over S1, which is fine. You can do that. That's just multiplication by 1. And now you want to answer this question. Okay, so what's the probability S2 over S1 times S1 over S0 is bigger than 1? All right, once again, we don't know how these guys by themselves, we know that these are log normal. So let's take the log of these, of both sides. So you have S2 over S1 times S1 over S0 is bigger than log of 1, which is 0. Okay, what can we do with this? Log of this, log of A times B is log A plus log B. So that's kind of nice. Now we've separated it. So you have this, and you know that this is normal. These are that one's normal. They're independent. So their sum is normal. What is the mean of each one? It is 0.0165. Each one has variance 0.0730 square. So you can subtract the mean of this sum, which is the sum of the means, divide by the standard deviation, and you have, so let's just write both of them, a normal with mean equals 0.0165 and sigma squared equals 0.0730 squared. Okay, each one. So the sum will have and variance is 2 times 0.0730 squared. Okay, so sigma will be square root 2 times 0.0730. So let's just subtract all that. Sorry, I'm running out of space there. All right, and now this guy, that is going to be normal 0, 1. So this is the probability of z being bigger than negative 0.033 over square root 2 times 0.0730. You work this out, and that is the same as probability z being bigger than some negative number. That's the same as the probability of, oops, z being less than minus of that number, which is plus. So z less than 0.033 over square root 2, 0.0730. So it's just phi of this number, and that is approximately 0.6524. Okay, so that's quite nice. You will see a log normal distribution many times in many applications. Okay. Okay, so the last thing we're going to look at over here in 6.3 is 6.3.4. This is Poisson binomial random variables. You will see that if you have two Poisson random variables that are independent and you add them, you will still have a Poisson random variables. And under certain conditions, the sum of binomial will also be binomial. Okay, so we'll take a look at that. Okay, so the proofs are in these examples. Okay, so let's look at some. So this is example, 3E, sums of independent Poisson. And this is just some kind of manipulation with sums and numbers, okay? So x and y are independent Poisson random variables with parameters lambda 1 and lambda 2 respectively. Okay. Find the distribution of x plus y. All right. So let's take a look. Now this is a discrete situation, so that's nice. We haven't done discrete examples. Okay. So let's look at the probability of x plus y equals n. Okay, now what's the range of x plus y? X plus y can be 0, 1, 2, 3. X can be 0, 1, 2, 3, dot, dot, dot. Y can be 0, 1, 2, 3, dot, dot, dot. Sums of whole numbers are whole numbers, and 0 plus 0, that's 0. So it's just x plus y has range non-negative integers. All right, so what's the probability x plus y equals n? Well, take an example. What's the probability x plus y equals 5? Well, x can be 0, y 5, x can be 1, y can be 4, x can be 2, y can be 3, and so on. X can be 5, y can be 0. So this is the same as you sum up from k equals 0 to n, the probability that x is k and y is n minus k, correct? Okay, and x and y are independent, so this probability will be the product of the probabilities. Okay, and let's write down using the Poisson distribution. What is this? It'll be e to the minus lambda 1 to the k over k factorial. This is e to the minus lambda 2 to the n minus k over n minus k factorial. Okay, and we can take out the exponentials. Let's do that because they've got nothing to do with the k's. Okay, so it's e to the minus lambda 1 times e to the minus lambda 2 that comes out, and add up the exponents, and this is what you have. Okay, and now what's left in the summation is lambda 1 to the k. Oops, let me write that nicer. Lambda 2 to the n minus k over k factorial and n minus k factorial. Okay, I'm gonna write it like that. All right, now what do we do with this? Let's take a look at this inside. When you look at the denominator, that looks a lot like n choose k, but there's no n factorial in the numerator. Okay, putting that in will actually help us be able to recognize what this is on the inside. So let's put in an n factorial, and because the and let's just, okay, multiply by n factorial over n factorial on the inside. Take out one of them and leave the one we need inside. Okay, now take a look at this. What do you recognize this as? You do know this. This is just the binomial expansion. So this is lambda 1 plus lambda 2 to the n. What do we have outside? E to the minus lambda 1 plus lambda 2. And over n factorial. Okay, let me write this a little bit. Okay, and what is this? This you know. This is exactly the probability of Poisson random variable with parameter lambda 1 plus lambda 2 equals n. This is the probability that a Poisson random variable lambda 1 plus lambda 2 equals n. Okay. All right. So that's what you have. If you have independent Poissons, add them up, you still have a Poisson random variable. Okay? And the next example, and that's the last one we're going to do in this section, is what happens when you add up independent binomials. It's very intuitive, so I mainly wanted to discuss that. The calculation manipulation is easy. You can take a look at that in the book. So in example, you have that, let's say x and y are independent binomial. X is binomial with parameters n and p. So it's n trials, each one has success of probability p. Y is a binomial random variable with m for Mike trials, same probability of success p. Then what can you tell me about x plus y? Well, how can you think about this? You can think about this as x is a random variable, n trials, each one has probability p of success, but each one is independent of the other, each one of these n's. Then after that, you're going to have another m trials, m for Mike, and each one has probability p of success. So together you can think of the whole thing as n plus m trials, each one has probability p of success. Okay, and that's exactly what you have. X plus y will be binomial n plus m with probability p of success. Okay, and if you want to look at the actual calculations, that was just a heuristic proof. For calculations, I want you to look at the book. Okay, and the page is 266, 267. All right, so I hope that made sense. And what happens when you add, main things you have to remember. How can you get, what does the density of x plus y look like? It's the integral of f sub y at y times f sub x at a minus y, y going from negative infinity to infinity. What happens when you add up two normal random variables? What happens when you add up Poisson random variables? And what a log normal random variable is. And what happens when you add up uniform random variables. Okay, so that's what we've looked at over here in this section. All right, I hope that made sense. Please email me if you have any questions. Okay, bye guys.